Hi students, today I am going to explain module 5, which is nothing but sequential circuits and fundamentals. In the previous chapter or module, so far we discussed about analog and digital analog electronics, and in the digital part the number systems and the combination circuits. In the previous module, module 4, we discussed about what is combination circuits and what are the examples of combinational circuits and design procedure for combination circuits. Now I'm going to explain the sequential circuits and its fundamentals. This is the syllabus. Basically, the syllabus has divided into two parts. In the first part, which consists of what is the difference between the combinational and sequential circuits, and then what are the basic elements in the sequential circuits, and it will start with the SR latch and flip-flops, and what are the different types of flip-flops, SR, JK and JK master slave, and D and T type flip-flops, and all these flip-flops can be explained by truth table, characteristic table, excitation table, and characteristic equation. So in the sequential circuit also, if you want to design any flip-flops, so we might have follow all those steps. And here there will be a conversion between flip-flops. So if you want to design one flip-flop by using other flip-flops, so these are all comes under first part. Once you have aware of all the basic fundamentals of sequential circuits or sequential elements, like basic memory element like flip-flops, so then with the help of those flip-flops, so you can design simple complex circuits, like simple sequential circuits like registers, counters. So that's why they have mentioned in the second part registers. So we are going to study about what are the different types of shift registers, and left shift and right shift and bidirectional shift registers, and then the counters comes under counters. So there are two different types of counters, asynchronous and asynchronous counters. In that, first, what is the counters and operation of counters, and by taking simple example of the state transition table and design for synchronous counters and asynchronous counters. So as we go through this module, initially we have studied the basic elements which are required to design a sequential circuits, and then we achieved we implemented synchronous and synchronous sequential circuits. So for the second year students, so it is enough that what are the basic fundamentals of sequential memory components, and then by which we can implement a simple sequential circuits. So in that way, we have to divide this syllabus into two parts in this module 5. Let us see what is sequential circuits, and then what is the block diagram, and what are the main basic fundamental differences between sequential and combinational circuits. If you see here, sequential circuits. What is sequential circuit? In the digital electronics, a circuit which consists of both combinational and memory elements is called sequential circuits. In other words, we can say like this: a sequential circuits in which the present output is depends on not only present input and also previous output. These previous outputs which comes from memory element. So which depends on the present output depends on present input and also previous output, then it is called sequential circuits. In contrast, in a combinational circuits, the present output depends upon only present input. As we know that, we were discussed in previous chapters. So as simple of as logic gates to as complex of some kind of circuits like mux, decoder, encoder, comparator. If we can see there, so we could observe that each and every circuits as simple of logic gates. If you take logic gate, a simple logic gate which consists of two input and one output. So for let us take, we can see here A and B are the two inputs, and Z or C is the output. Like Z is the output. So when we have seen this simple logic gate and gate, which represents the product term. So the Z out present output directly, which depends upon present input, which we have given at the A and B. So not only this simple logic gate, if you see any complex circuit like a muxer, so in this case I am taking only block diagram instead of taking circuit diagram. This is the block diagram for muxer. We know that a muxer, for example, a muxer input bus having 4, and based on this input, number of select lines are 2 select lines. These are the select lines, these are the inputs, and we can get some output. So here also this single output, 4:1, 4 primary inputs and 2 select lines and 1 primary output. So this output mainly depends upon present inputs, whatever the input and present selected inputs, and there will be no, and there was no any previous output which is come back to the input and then which will propagate to the circuit and then will give some other output. So that's why it is a combination. If you take any combination circuits, whether it is if you take multi-level gates, not only single level, multi-level gates, the entire combinational circuit which depends on present output depends on present input only. As we can see here in the sequential circuit, the block diagram, this is nothing but combinational circuits in the sequential circuits. So if you see any sequential circuit which consists of combinational circuits like gates and sometimes we use decoder, sometimes we use some kind of combination circuits along with the memory elements. So this the main primary input to the combinational circuit is, the first one is the primary input coming from external, and then other input is which is coming from the memory element. So the output of the memory element which is come back to the input to the combination circuits. So that the main primary inputs to the combination circuits are main external inputs and the output of the previous output from the memory element. So this then we can collect the output from this combinational circuit. So likewise, we can observe that a sequential circuit which consists of combinational and memory elements. So when I am talking about memory elements, how can we make this memory element from these digital circuits? If you see here, memory elements which can store one bit of information. Right now we can make with this like some kind of circuits. So what is the basic fundamental for any memory element? If you see any basic circuit, let us take inverter. If you see here, the output of the inverter take back to the input, then I am giving 0, the inverter output is 1, that 1 again feedback to input, like an input. So then if we take two inverters, so 0 output of one inverter is 1, that 1 is passing through the further inverter and it will get 0, that 0 again get back to input, same 0 is passing through the 2, passing through these two followers of inverters, then you will achieve the same output. We can maintain the same 0, so that we can call it as we can resemble this as which can store the logic 0. So we feel it as memory. So but this single input not at all prefer for creating the memory. So that's why we can we can use the 2 input logic gates to make the memory element. So let us see that what is the basic building block, and then how can we make this basic building block for memory. Let us take latch, SR latch. When we come to latch is a sequential circuit, basic sequential circuit, which will make that the circuit can be as a memory element. And when we see this, basically this memory element is like a bistable multivibrator. It has two stable states. So that's why it's called bistable multivibrator. So, but here, this is we can see the two different diagrams for SR latch. So basically, latch is made with a cross-coupled of two NOR gates or cross-coupled of two AND gates. So if first consider this first figure, if I am taking two NOR gates, these two NOR gates, a 2 input 2 NOR gates. So one input is directly giving to reset input, and a second NOR gate, one input is directly giving to set input. The output of the first NOR gate is cross coupled to the input of the second NOR gate, and the output of second NOR gate is get back to the input of first NOR gate. So this kind of cross coupled of NOR gates will make use of the memory storage of digital values, logic either 0 or 1. Similarly, we can make the same memory element with the help of NAND gates. So instead of using NOR gates, then we can use NAND gate. So here also same, there are two primary inputs, set and reset. So that's why it is called SR latch. S means set and R means reset. And then there are two NAND gates. Again, the primary inputs have given S and R inputs, and then we can cross coupled of that outputs, primary outputs. So Q and Q bar, the Q is connected back to the second NOT gate, NAND gate, and Q bar output is connected back to the first NAND gate. So if you observe that any latch, like either NOR latch and NAND latch, it has two inputs, primary inputs, set and reset, and it has two primary outputs. But you remember that the primary outputs are always complement to each other. So whenever the output not complemented to each other, which means that it is the state is in forbidden, or it is it is not considered that particular output. So remember that latch has two outputs which are complement to each other. but we can, for the sake of understanding of that memory, so we can consider the primary output like Q. The complementary output we can't consider. Let us see that the simple operation of SR latch by considering this primary input S and R. So in order to understanding this SR latch, we can take that truth table and then characteristic table. If you see truth table, that means what are the inputs and what are the outputs. So here we can take this S input and R input and Q with Q bar, Q and Q bar. So here whenever the S0, R0, when I am considering the S0, R0, we can't say that what is the output for NOR gate, because NOR gate is logic 1 enabled. When one input is 1, which automatically enable the output. So where NAND gates, logic 0 enabled. So when it is enabled, like logic, whenever any one input is 0, you can automatically it will enable. So likewise here in the NOR gate, when S is 0, R 0, we can't say that what will be the output. So now in this case we can assume, or we can initialize that we are assume that output is the Q. For example, the Q output is 0. When we assume that Q is 0, automatically Q bar is 1. So this assumption will make that output will get some output after some time. So this assumption of Q is equal to 0 means that 0 is available at this input. So then now it is enough, 2 inputs are enough, will get the output of second NOR gate. The 2 inputs 0 and 0 will make the NOR gate to logic 1. These are the assumption 0 and 1, but after giving this assumption, then this 0 will come here and then you will get the next state is 1. This one immediately appear across this one input 0 and 1 of the NOR gate 1, which make the output is 0. So initially I am assuming that 0 in the Q, 1 in the Q bar. After applying S and S0, R0, that the next one is also, the next output is 0, Q is 0 and the Q bar is 1. What does it mean? Which means that I am assuming 0 and 1 in the Q and Q bar, but again after applying 0 and 0 in the SR latch, it won't change. So we can call it as no change condition, no change state. No change state. Suppose just I am triggering that set input or reset input logic 1 and by keeping reset with the 0. So what happened in this case? Even though if you assume, in the previous case, even though if you are assuming this initial value is 1, after applying the 0, 0, you will get 1 in the Q and 0 in the Q bar. So that's why in both cases, we assume both cases, either 0 or 1, you will get the same output by giving the S and R as a zeros. Now, just we can change the 1 logic for S, logic 1, and keep constant of R is equal to 0. What happened when S is equal to 1? When S is equal to 1, automatically this NOR gate will, without depending on the second input, automatically that output will make 0, because we know that NOR gate like a R plus NOT gate. So any one input is 1 in the OR gate, logic high, but NOR gate is complemented of that output. So any one input is 1, OR gate is like 1 and its complement is 0. So NOR gate, one input is 1, for NOR gate the output will be 0 automatically. So this 0 immediately appear across this one, 0 with NOR gate, 0 0 NOR gate is, you will get logic 1. So that means when S is equal to 1, R is equal to 0, that Q value is 1 and Q bar automatically 0. So which state is called set state. The output Q going into set state when S is equal to 1 and R is equal to 0 in the NOR latch. S is equal to 0, R is equal to 1. What happened? By checking now and before considering this case, let us take the memory cell action. Now again I return to this set value is written to 0 and R is already 0. What happened? So when S is equal to 0, R is equal to 0, previously the Q is 1 and Q bar is 0. Now after return back to this set pulse is to 0. So we know that S is 0, R 0, whatever the previous output, the same output will be existed at the output. So because S is 0, R 0 means no change. So this kind of action is called memory. So S is 0, R 0, after again return back to S is equal to 0, then the same output, previous output is maintained. This kind of action is called memory. So that's why we can use this latch as a memory by maintaining the inputs as a 0 0 in the SR latch, NOR latch. Now again we can have some memory value 1 and 0. Now I am setting set logic 1 to reset and logic 0 for set. So R is equal to 1, S is equal to 0. Immediately the output Q value is 0 because the one input is 1 in the NOR gate. You will get 0. That 0 available in this second input of NOR gate 2, which will make the NOR gate 2 as a 1, logic 1. So Q is equal to 0 and Q bar is equal to 1, which means that we can focus on Q only, not Q bar. So it will make that the latch is in reset mode or reset state. If I am giving, for example, if I am again change to original state, like set value 1 to 0 and set already 0, then it will have same state like 0 and 1. So which is nothing but memory. Okay, 0 0, we can have 0 and 1. And again if I am turning this S is equal to 1 and R is equal to 1, we know that one input is 1, that NOR gate is equal to output is 0. So if S is equal to 1, R is equal to 1, immediately that output value 0 0, but it is violate the condition of sequential circuit like latch and flip-flops. So both outputs must be complement to each other, but here when applying 1 and 1 in the SR latch, so it will get 0 and 0, so which is nothing but forbidden. Okay, so which is not allowed. So both outputs are same, which is not allowed. So simply we can say that in the latch, SR latch, whenever NOR latch, as long as you keep S and R is zeros, that the output remains same, which maintain the same output, which will lead to store a logic values in the Q and the Q bar. Similarly, if you see here in the NAND latch, the same thing, but a small change. The output is changes by changing the S and R. In this case, S and R and Q bar. So now I am directly writing what happened when S is equal to 0 and 0. When S is 0 or 0, we know that NAND gate, any one input is 0. Immediately we can say that output is 1 without analyzing, without assumption. Output is 1, 1. So it is violation of this latch operation. So that's why we can't construct this 0, 0 in the NAND latch. What happened when S turn to S, for example, R is equal to 1. When R is equal to 1, S is equal to 0. As we know that one input is 0, immediately output is 1. That our output 1 is available here. 1 into 1 and complement its complement. 2 inputs are 1 in the NAND gate. The output will be 0. So, sorry. Yes. This when 0, 0, 1 input, you will get the 1 in the Q and the 0 in the Q bar, which is called set in the NAND latch. And when I am giving 1, 0, you will get a 0, 1 in the reset mode. If I am giving, for example, if I am turned to this set to 0, sorry, next case is this S is equal to 1, turn to this R is equal to 1 and 1, 1. So when both are 1 in the NAND latch, when both are 1 in the NAND latch, we can't decide that what is the output. So in the NAND latch, you can't decide. So now by applying the assumption, so by assuming that it is logic 0 or logic 1. For example, if it is logic 0 or logic 1. If it is logic 0, that 0 available here, 1 into 0 in the NAND gate will get a 1. That 1 is available, 1 and 1, 1 for NAND gate, automatically that 0. So previously we assume that 0, now we can get the 0 output. 1 to 1. Or otherwise we can apply, we assume that initially the latch has a one output, one state in the queue. That 1 is available here, 1 into 1 is nothing but initially 0. If it is 1, Q bar is 0. So 1 into 1 like 0. That 0 available here, 0 into 1 like 1. So previously 1 in the queue, 0 in the Q bar. Now after applying 1, 1 in the NAND gate, you can get 1 and 0. So nothing but 1 to 1, 0 to 0. No change. So for 1, 1 in the NAND latch, we can have no change in the output. Whatever the previous output here, this one. So we can have no change. Not only 0, if it is 1, we can have 1 in the queue and 0 in the Q bar. No change. We can also easily remember, students, like a truth table, two variable truth table, 0, 0 combination, 0, 1, like two variable combination, 0, 0, 0, 1, 1, 0, 1, 1 is the inputs, and output if consider only Q, okay, 0, 0 for NAND, like Q and Q bar, 0, 0 violation, forbidden, not allowed condition, 0, 1 wherever the logic 0 is like 0, because 0 is the enabled input for the NAND gate, so 0 is which make the enable. So in the NAND latch, wherever 0 under S and 1 under R, which will make the set, and 1, 0, 0 under R, we can make the reset. 1, 1, no change. So no change, set, reset, violation. In the NOR latch, easily remember, first case 0, 0, no change, 0, 1, reset, 1, 0, set, 1, 1, forbidden. Likewise, we can remember. This action is most important to understand how the latch has acted as a memory element. Then we can easily modify this diagram for further, further topics like flip-flops. So by adding extra circuits. by gated circuit for in front of this S and R latch. So when we see here, there will be no controlling. So when we want to get the set, when we want to get the reset, whenever we don't want that output goes to set or reset, uh, we don't have any controlling. So for example, that output Q must be in set. So whenever inputs are changes, we can't control. If I am stopped at a particular time, the output remains same state. So we can't control, because whenever R and S are changes, the output automatically changes, which is not which is not expected and which is not required. So if you want to hold some time, no need to change the output. You just keep that whatever the change in the input, but you can keep remain the same in the output. You have to add the additional circuit in front of this latch. Then we will achieve this flip flop. Okay, let us move to the flip flop. So remember these two tables, then we can use of them to understand in the flip flops. Now coming to the flip flop. Flip flop is a sequential circuit which can store the binary information of logic 0 or 1, and then by just extra adding to this gated circuits like NAND gate, two NAND gates are connected with same S and R, connected with the two NAND gates with a common pulse common clock circuit. So when we connecting this common clock, then this clock will uh, will control the whether the input, what the passing inputs are, make them the latch to change the state. If you don't want to change the state, then whenever the clock is off, when the clock is low, then automatically that entire flip flop is in unchanged mode. So let us see the simple NAND latch. We know that NAND latch, uh, actual NAND latch operation. But once you finish it up this SR flip flop truth table, then finally you remember this SR flip flop truth table, not remember the latch. Now let us see that what is that. So this SR latch, how it can be act as a gate, a gated circuit. We know that NAND gate, whenever any pulse the clock pulse shape, okay, high low, logic 1 and logic 0. Whenever clock is low, which act like directly, so the output will get 1 and 1. What about the 1 for the NAND gate? No change. So it won't change any output. So when giving active low or low state in the clock, the output won't change. Whenever clock is high, these two inputs, clock inputs, are passing to the two NAND gates, then which depends on the S and R. Whenever clock is enabled or clock is high, then which will depends on the whatever the S and R are input passing through the latch, passing through this gate and then allow. That's why it is which allows the whenever clock is high, then which allows S and R inputs to the latch. So now let us see that by combining all these gated circuit, we can call it as flip flop, SR flip flop. Now let us see the simple truth table and then characteristic table and then characteristic equation for SR flip flop. As you know that now we can consider extra input like clock controlling input. So whenever clock is 0, assume that it is a level triggered clock. So whenever clock is 0, irrespective of S and R, output unchanged, whatever the inputs. Okay. So then whenever clock is high, then the actual truth table starting. When clock is 1, then which depends on S and R. When S is 0, R 0. S is 0, R 0. So 0 into 1, output is 1. 0 into 1, output 1. Like now, we know that NAND get any one input is 0, output automatically 1. So we know that NAND latch when 1 1, okay, in the NAND latch 1 1, what does it mean 1 1? Unchanged means memory, unchanged. Unchanged or remain the same previous state. So whenever 0 0 actual inputs are 0 0, it indirectly means the Q is previous state, unchanged or memory. Okay, just to we assume that, for example, initially Q is 0, that 0 is available, and already we have 1 1 here. So 0 into 1 output is 1, output is 1, that 1 is available here, 1 into 1 and bar is nothing but 0, we can get the 0. So initially we assume that 0, we will get 0. Whenever assume this one is 0 means this one is 1, again we will get the logic 1 output in the keyboard. So 0 to 0. If you assume otherwise, if you assume 1 1 also, we can get the same 1 output. So SR flip flop, SR NAND flip flop, 0 0 out remains same. 0 1, when clock is high, 0 1, this logic 1 corresponding to under reset column, so we can call it as a reset. Under 1 0, the 1 is under S, the output will be set. 1 1 1, forbidden case. Let us see forbidden case. So clock is high, clock is high. As long as clock is high, then which whatever the inputs S and R, then which allows the gate S1 R1, 1 and like NAND gate 1 1 means 0, NAND gate 1 1 means 0. So this 0 immediately NAND gate, we can directly say that what is output NAND gate, 1 input is 1, output automatically 1, output automatically 1. So this uncomplemented outputs appear across the Q and Q bar, which makes the forbidden case. So simply for the NAND flip flop 0 0 unchanged and 0 1 reset, 1 0 set mode and 1 1 forbidden case. This is the characteristic table. Characteristic table is the table which gives the relationship between main inputs S and R and what is present state. After applying the S and R, what will be the next state? And then we can make the characteristic equation. So let us assume that in S is equal to 0, R is equal to 0. Now the flip flop at present state is 0. You assume that flip flop is presently 0, present state. After applying S0 R0, you will get the same 0 because under 0 0 condition, the SR flip flop NAND flip flop is unchanged. 0 0 memory are unchanged. Suppose that present state is 1, same I am applying the 0 0, again the next state is also 1. If present state is 0, I am applying, changing that reset to 0 to 1 pulse, 0 to 1, that means 0 0 and 1 in the inputs. S is equal to 0, R is equal to 1. We know that we remember 0 0 unchanged or memory, 0 1 reset, 1 0 set, 1 1 forbidden. So 0 1 means automatically that next state will get to reset. Reset means logic 0. So if it is initially 0, it will be remain the same reset to 0, or if the present state is 1, it will get to reset to 0. So 0. So by default 0. Suppose our present output is 1, but I am giving 0 1 case. So the output is reset. So this 1 will be changed to 0 because the output will change to reset mode. And initially present output 0, I am applying 1 0 set. which will make the output set. Suppose initially the output is 1, I am applying 1 0, again it will get to set 1 2 1. Present state is 0, my inputs are S and R 1 1, so according to 1 1 it is a forbidden case, so you will get the forbidden output 1 1, whatever the output 0, all zeros, 1 all 1, 2 ones. So for 1 1 case, whatever the present state, you will get a forbidden case in the characteristic table. So what is the characteristic equation? How to get a characteristic equation with the help of K-map? If I am considering the 3 variable inputs, assume the 3 variable inputs, S and R the actual inputs and Q is the present state. So we will get the next state equation. We will consider Q and S and R. Take the 3 variables and take 3 variable K-map S R Q, S in R, R0 0 0 1 1 1 1 0, RQ in column wise and S is in row wise 0 and 1. So where will be the logic one for the Qn plus 1? So 0 0 1 0 0 0 1, and where will be the 1 1 double 0 1 double 0, and another one 1 not 1 1 not 1. And this forbidden case we can consider that don't care 1 1 0, don't care 1 1 don't care. So we can use this K-map with don't care and make the prime implicants for this quad like 4 ones, and 1 1 is left. In order to cover that one, we can make pair, so that there are 2 prime implicants. The answer for these 2 prime implicants is first box. This is first one, this is second one. The first box equation is, it is S is equal to 1, S bar. So this entire row is covered, so no value is coming at the vertically. Only we can consider S is equal to 1. This is the term S, only one term, plus this pair, so which covers S and S bar cancel to each other. What will be the vertical box line? 0 and 1. That minterm is 0 and 1 means R bar Q, R bar Q. So this is the characteristic equation. This is characteristic table. This is characteristic equation. The characteristic equation for SR flip-flop is S plus R bar Q. So with the help of, so then in this, the present output depends on present inputs S and R bar, and Q is the previous output. So that's why it is a sequential circuit. And if you see this, likewise JK flip-flop, see small change in the JK flip-flop. So what happened? By considering the SR flip-flop, the output of this Q is connected back to the gated NAND gate of the one of the input, so that it will become 3 input NAND gate, and the Q bar is connected back to J, like this first NAND gate. So Q is connected to K type gate and Q bar is connected to J. Then it is said to be JK flip-flop. So now if you see this diagram, what will happen in this truth table? In the truth table, so when clock is not, like when the clock is 0 or 1 to 0, irrespective of J and K, it is in previous state or unchanged. So previous state. Whenever clock is high in the flip-flop, then which will depends on J and K. So here initially, indirectly J is nothing but S, K is nothing but R. So we know that SR flip-flop, NAND flip-flop, but extra point is because of this connected feedback connection. So the entire truth table for J and JK flip flop is same except the 1-1 case. In order to avoid the forbidden case, which is which was occurred in this SR flip flop, it is eliminated by the JK flip flop. Okay. So let us consider the one case when clock is high, J0, K0, J0, K0. Clock is high, 1, 1, 1, 1. So NAND get any one input is 0, output is 1, 1. SR is equal to 1, 1 in the NAND gate, in the NAND this one. So 1, 1 means which depends on the other input. So assume that Q is 0. When Q is 0, this one is 0. 0 into 1, 1. When Q is 0, Q bar is 1. And this 0 is available here. 0 into 1. Then this is 1. And this one is available here. And 1 into 1 bar in the NAND gate, you will get 0. So same output. 0 becomes 0 and 1 becomes 1. Unchanged. So this case 0, 0 unchanged. So previous state or unchanged state, no change state. 0, 1 like similar in the SR flip flop. Reset 1, 0 set. What happened when 1, 1? Because of this connection. What happened in the 1, 1? So when 1, 1, 1, 1, J is equal to 1, clock is high. So in this 1, 1, which depends on third input. Directly we can't say that what is output. So this third, we don't know third input. So assume that here. Assume that Q is equal to 0. When Q is equal to 0, this feedback connection will make that 0. Then automatically that NAND get 1. So R is equal to 1. So when Q is equal to 1 means Q bar is equal to, Q is equal to 0 means Q bar is equal to 1. That feedback connection make that this third input is 0 or 1. So all triple 1 in the NAND gate means you will get 0. So 0 and 1 are passing through the latch. So then which makes that one input is 0 in the NAND gate, you will get automatically 1. That 1 is available here. 1 into 1 automatically that 1 is 0. So 0 becomes 1, 1 becomes 0 in the Q bar. So this is called complement. So we'll get toggle output. Even in the, we can apply the same opposite case. Assume that if it is 0, if it is 1, logic 1 in the output, you will get applying the same thing. You can get the logic 0 after applying the 1, 1 in the J and 1, 1 in the JK inputs. So likewise in the JK 1 and 1 or 1, 1 inputs, the output will get toggle with the previous output. This is the characteristic table. So by applying the same thing, we can get the same table with this SR flip flop. Assume that initially 0 and S0, sorry, J0, K0. So unchanged previous state. If it's 1, 0, 0 unchanged previous one. If it is presently initially 0, my input is J and K inputs J0, K1, which means a reset. Even though the output is 1 in the previous reset, you will get the reset. Likewise, same truth table, characteristic table, which is available in this SR flip flop, except last two cases. If you assume that present state is 0, my inputs are both 1, 1. Now in this case, I am getting toggle output in the next case. If I assume that 1 is in the present state, J and 1, 1 will get 0. So this is toggle output. This is set output. This is reset output. This is unchanged output. This table, characteristic table, will help to find out the characteristic equation with the help of K-map. J, K, Q 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. By considering all the logic 1 in this, in the next state, Qn plus 1. So this is for Qn plus 1 table. Okay, this is characteristic equation, characteristic table. So this is a logic 1. Wherever the logic 1, that combination make put 1 in the boxes, square boxes. 001, 001, and 100, 1, 101, 1, and 110, 110, logic 1, 111, logic 0. Sorry, you no need to. So only 3 ones, 4 ones are there. 4 ones are I mentioned. So now consider this one is 1, this one is 1. So what is the Boolean function for this one? For this one, q j, this is nothing but j, and what is the common one in the these two columns is like q bar, j q bar. So first term will get first term j q bar, and this one, what is the Boolean function, minimized Boolean function for this pair? Nothing but in the row wise these two are cancelled, j and j bar and j are cancelled, only we can consider 0 1. 0 1 means k bar and q. 0 represents k bar, 1 means q, k bar. So we'll get a characteristic equation. Likewise, we will get the characteristic equation for j k flip flop. So in this way, j and k are inputs, primary input q and q bar are the previous outputs. So if you want to get the next state output, which depends on present inputs and also previous outputs, so it is sequence circuits. The characteristic equation for jk flip flop is j q bar plus k bar q. So in this way, we can have the sequence circuits. So by studying the basic latch as a memory elements, then we can modify that circuit into flip flops. So there are different kinds of flip flops: SR flip flop, JK flip flop, T flip flop, D flip flop. So the main flip flops will be discussed in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.